On Monday, we discussed polynomials and we defined primitive roots. So what we proved for polynomials is the division algorithm. And that just tells us that what you learned in high school about how to divide one polynomial by another always works. And we defined a primitive root mod m. So this is defined as follows. We take an integer m and we look at the congruence classes mod m, and Z mod m star is the set of all congruence classes where A and M are relatively prime. And we proved previously that if one element of a congruence class is relatively prime to M, then every integer in that congruence class is relatively prime to M. So this definition makes sense. And the number of congruence classes relatively prime to M, that is the order, the number of elements in this set is exactly the Euler phi function. And Z mod MZ is a multiplicative group. And if we take an element A, an integer A, such that A and M are relatively prime, then we know by Euler's theorem that A to the positive integer phi of M is congruent to 1 mod M. In terms of congruence classes, this is exactly the same as saying that if you take the congruence class A plus MZ and you raise it to the power phi of M, this is A to the phi of M plus MZ, which is 1 plus MZ. So this, in this group of congruence classes relatively prime to M, the congruence class A plus MZ to the phi of M is equal to the identity. And we say that A has exponent D modulo M if A to the D is congruent to 1 mod M, and D is the smallest positive integer with this property. Equivalently, A has exponent D modulo M means that A plus MZ to the power D, which is A to the D plus MZ, is 1 plus MZ. And D is the order of the congruence class A plus MZ in the group Z mod MZ star. That is, the order of an element in a group is the smallest positive power of the element that's equal to the identity. Elements don't always have finite order, but in a finite group they do. Okay. And we gave some examples. Suppose we let M be equal to 7, then 3 is a primitive root mod 7. Remember, what is a primitive root? Sorry, I didn't state the definition, so let me do that now. So a primitive root mod m is an integer a such that a and m are relatively prime, and a has order phi of m modulo m. That means the powers of a to the 0, sorry, the positive powers a, which is a to the power 1, a squared, a cubed, up to a to the phi of m minus 1. These are distinct, and a to the phi of m, that's equal to 1, congruent to 1 mod m. So these phi of m integers, these phi of m positive integers, they're all relatively prime to m. So they represent every congruence class modulo m. So an example is to take m equals 7. Phi of 7 is 6. What are the powers of 3? 3 to the first power is 3 mod 7. 3 squared is 9, which is 2 mod 7. 3 cubed is 3 times 3 squared. 3 times 2 is 6. 3 to the fourth power is 3 times 6 is 24, is 3 mod 7. Oops. Let's see, something's not right here. 3 to the fourth. 3 to the first power is 3. 3 squared is 9, is 2 mod 7. 3 cubed is 27, which is 6 mod 7. 3 to the fourth is 18, which is congruent to 4 mod 7. 3 to the fifth is 12, which is congruent to 5. This is all mod 7. And 3 to the sixth is 15, is congruent to 1 mod 7. So as we take higher and higher powers of 3, what are the powers of 3? 3, 9, 27, 81, 243, 729. But when you reduce the mod 7, you get 3, 2, 6, 4, 5, 1. That is, you have all the integers 1, 2, 3, 4, 5, 6. Those are exactly representatives of the congruence classes relatively prime to 7. So 3 is a primitive root mod 7. Another way of saying that is the order of 3 plus 7z in the group z mod 7z star is 6. Suppose we take m equal to 8. So z mod 8z star, this is the set of congruence classes relatively prime to 8. There are 4 of them. 1 plus 8z, 3 plus 8z, 5 plus 8z, 7 plus 8z. But if we check, so 1 to the first power is congruent to 1 mod 8. So 1 has order 1 mod 8. That's the smallest power, positive power of 1 congruent to 1. 3 squared is 9, is congruent to 1 mod 8. So 2 has order 2 mod 8. 5 squared is 25, is congruent to 1 mod 8. So 5 has order 2 mod 8. 7 squared is 49, is congruent to 1 mod 8. So 7 has order 2 mod 8. But phi of 8 is equal to 4. So there's no element in this group of congruence classes mod 8 that has order 4. So there exists no primitive root modulo 8. So not every modulus has a primitive root. And the big theorem about primitive roots that we'll prove next week for every prime p, there exists at least one primitive root modulo p. Actually, I think we'll prove that theorem today. Now, what's another way of saying this? So if we have a group G, so remember a group is a set with some multiplication that's associative. There's an identity element. Every element has an inverse. And if the group is abelian, then AB is BA for all A and B. So we have a group G. Let's recall the order of an element A in G is the smallest positive integer D, such that A to the D is the identity. Right? That's the order of an element in a group. So our fundamental example is if we take the group G to be the multiplicative group of congruence classes mod M that are relatively prime to M. A group G is cyclic if there exists an element A in the group such that G is the set of all powers of A, positive and negative. That is A to the 0, which is the identity, A squared, A cubed, and so forth. A inverse squared, which you write as A to the minus 2, A to the minus 3, and so on. So it looks like an infinite sequence of elements, but they're not necessarily distinct. You can have a finite group or an infinite group. But a group is cyclic if there's an A in G, so that G is all the powers of A. And we just saw an example. If we take G to be the multiplicative group of congruence classes mod 7 that are relatively prime to 7, this is cyclic. And an element A with this property is called a generator of the group. And if we take 3 plus 7z, this generates G, because the set of powers of 3 plus 7z 1, 2, 3, 4, 5, and 6, we saw that this gives you every congruence class mod 7. So a primitive root modulo m is a generator of the group of congruence classes relatively prime to m. And the reason why for every prime p, there exists a primitive root mod p is because, as you know, because we proved it, and it was even on the last exam, for every prime p, the congruence classes z mod pz is a field. It's not just a ring, not just a commutative ring. It's a commutative ring in which every non-zero element has a multiplicative inverse. That means it's a field. We proved that. And so this will be a special case of the following theorem, that G be a finite subgroup of the multiplicative group of a field. Then G is cyclic. Now, if the field is finite, the multiplicative group is finite, and every subgroup of it will be finite, of course. So if you take a prime P, Z mod PZ is a field, the multiplicative group of this field is the set of all P minus 1 non-zero congruence classes. That's a finite set. Let's see. So to prove this, well, I need to say something about polynomials. I proved the main theorem on Monday. Let me just review that, and then I'll come back to this. So what we proved on Monday, this was theorem 3.1. That was the division algorithm. For polynomials. So you take F to be a field, that's important. And f of x and d of x are polynomials with coefficients in f. That's f square bracket x, means the set of all polynomials with coefficients in the field f. And d of x is not the zero polynomial. 0 is a polynomial, but d of x, what we're dividing by, is non-zero. So there exist, so existence, uniqueness, there exists unique polynomials q of x and r of x, such that f of x, if you divide it by d of x, you get a quotient q of x and a remainder r of x. And this remainder r of x is either the zero polynomial or the degree of r of x is strictly less than the degree of what we're dividing by, d of x. Right? That's just the division algorithm for polynomials. And there's actually a corollary of this, which I'll state right now, because we're going to use it. This is theorem 3.2. Theorem 3.2 says if we take a polynomial f of x, which is not zero, and let capital N0 of f be the number of distinct zeros of f of x. So a is a zero of f of x, just means f of a is zero. Right? Zero of a polynomial is just a number that when you stick it into the polynomial, you get zero. So you spend a lot of time in high school algebra, pre-calc, calculus, finding zeros of polynomials. Then the number of zeros of f is at most the degree of f of x. So this is why you know that a quadratic polynomial, it may not have any roots, it may have one root, it may have two roots, but it can't have three different roots, because the degree of a quadratic is 2 and the number of zeros is at most 2. So the proof uses the division algorithm. If we let alpha be any element of the field and let d of x equal x minus alpha. So if you take f of x and you divide it by x minus alpha, you get x minus alpha times some quotient plus a remainder, where either r of x equals 0 or the degree of r of x is less than the degree of f. Sorry, less than the degree of x minus alpha. What you're dividing by is x minus alpha. But x minus alpha, this is a linear polynomial. The degree of x minus alpha is 1. So to say that the degree of r of x is less than the degree of d means it's less than 1. And what integers, non-negative integers, are less than 1? Just 0. So either r of x equals 0 or the degree of r of x is 0. What polynomials have degree 0? R of x is equal to some non-zero constant. So if you take f of x and you divide it by x minus alpha, you get a quotient plus a remainder, which is a constant. Could be 0, couldn't be non-zero. But what is this constant? If you let x equal alpha, you get f of alpha is alpha minus alpha q of alpha plus r naught. Alpha minus alpha is 0. So r naught is just the value of f, the polynomial of f, evaluated at alpha. If you take f of x, divide it by x minus alpha, you get q of x plus f of alpha. And if alpha is a 0 of the polynomial f, which means f of alpha equals 0, then f of x is x minus alpha q of x plus 0. So if alpha is a 0, x minus alpha divides f of x. So now you might see what's going on. X minus alpha divides f of x. If you had another 0 beta, x minus beta would also divide f of x, and so on. But let me just write that out in detail. So we're going to prove the theorem by induction on n, which is the degree of f of x. If n is 0, which is the degree of f of x, then f of x is a non-zero constant. And the number of zeros of f is going to be 0, which is less than or equal to the degree of f. If n is 1, that means f of x is linear. F of x is a polynomial. We can write it as a0 plus a1x, with a1 not 0, right? This is every linear polynomial looks like this. And this is equal to 0 if and only if x is, well, just solving the equation. A0 plus a1x equals 0. X is equal to minus a0 over a1. There's exactly 1 0. So n0 of f is equal to 1, which is less than the degree of f. So assume that the theorem is true. We're proving this by induction. For polynomials of all degrees up to n minus 1, that f of x have degree n. If this polynomial has no zeros, we're done. Because 0 is less than n. If n0 of f is at least 1, that means it has a 0, let alpha be a 0 of f of x. So then we know that x minus alpha divides f. So f of x is x minus alpha times q of x for some polynomial q. And the degree of q of x is n minus 1, because f has degree n. This is degree 1, so this has to have degree n minus 1. If beta is a 0 of f, and f of beta, what is f of beta? Beta minus alpha q of beta is 0, then, so if a beta is a 0 of f and it's not equal to alpha, this isn't 0, so q of beta is 0. So the only zeros of f other than alpha have to be zeros of q. Q has degree n minus 1. By the induction hypothesis, n0 of q is at most n minus 1. So n0 of f, the zeros of f are alpha plus the zeros of q at most n. So that is a very nice proof. So this is serious mathematical reasoning, and you need to really spend a lot of time at home studying this and thinking about it. So how do I get from that to my theorem? Remember, this is the theorem I want to prove. Theorem 3.3, which says that let G be a finite subgroup of the multiplicative group of a field. Then G is cyclic. So the proof goes as follows. Let the order of G be M. So M is a finite subgroup, and we let M be the number of elements in this finite subgroup. So in chapter 2, theorem 215 is Lagrange's theorem. Which says that the order, that means the number of elements of a subgroup of a finite group, always divides the order of the group. So we're going to use this fact. So let A be an element of G. So the order of A, what is that? It's the smallest power of A equal to the identity. So this is the order of the cyclic subgroup of G generated by A. That is, if A has order D, then A squared, A cubed, A to the D minus 1, and E, that's the cyclic subgroup generated by A. And it divides the order of the group. So for every element in G, the order of A is the order of the cyclic subgroup of G generated by A. And so the order of A, that integer, divides M. It's a divisor of M. So the only orders of elements of a group are divisors of the order of the group, if the group is finite. So let D be a divisor of M, and let psi of D be the number of elements of the group G of order M. So we have a group G. You take a divisor of its order, and psi of D is the number of elements of the group of order M. Now, if psi of D is not 0, then G contains an element A of order D. And every element of the cyclic subgroup generated by A, I'll write it A in square brackets. This is A squared up to A to the D minus 1. Every element that's called B of this group satisfies B to the D is the identity. Now, we proved that in a field, a polynomial has at most its degree number of zeros. So consider the polynomial f of x equals x to the D minus 1 in the field f of x. This has at most D zeros. But every element in the cyclic subgroup generated by A, I'll write the identity as 1, A squared up to A to the D minus 1 is a 0 of F. So every 0 of F must belong to this cyclic subgroup. So every element of G of order D belongs to the cyclic subgroup. But by another theorem from chapter 2, a cyclic subgroup of order D is exactly phi of D generators. So you take this take a divisor D of M, look at the polynomial x to the D minus 1. What is D? You take an element A in this finite group. It has order D where D divides M. You look at the cyclic subgroup. Every element in this cyclic subgroup is a 0 of this polynomial. So every element of order, every 0 is in this subgroup. So every element in the group of order D is in this subgroup. but an element of the subgroup of order D is a generator of the subgroup. So they're exactly phi of D generators. So psi of D, which is the number of elements of G of order D, there are only two possibilities. Either it's 0, there is no element of order D, or it's phi of D. If there's at least one, there's exactly phi of D, elements of order D. And every element of the group has some order. So if I sum psi of D for all divisors of M, that's equal to the order of the group. But we also proved the theorem that summation phi of D over all divisors of M is equal to M. And psi of D is either 0 or it's phi of D. If any of these psi of D's is 0, this sum would be smaller than this sum. So we get that psi of D is phi of D for all D. In particular, psi of M is phi of M. It's greater than or equal to 1. So remember, what is M? M is the order of the group G. And this says the number of generators, number of elements of order M, is exactly phi of M. So in particular, there's at least one generator, and the subgroup G of the field F is cyclic. So the important case of that for us is when we take P prime, the field to be the integers mod P, the group to be the non-zero congruence classes of Z mod PZ. The order of G is P minus 1. So G, which is Z mod PZ star, not only is cyclic, but we know exactly how many generators it has. It has phi of P minus 1 generators. So this is theorem 3.4. For every prime P, there are exactly phi of P minus 1 primitive roots. So for example, if we take P as 7, P minus 1 is 6, phi of P minus 1 is phi of 6 is 2. So there are exactly 2 primitive roots mod 7. And one of them we saw was 3. And I bet the other one is 5. Let's see. 5 to the first power is 5 mod 7. 5 squared is 25, which is 4 mod 7. 5 cubed is 125. Or it's 5 times 4, which is 20, but in any case, it's 6 mod 7. 5 to the fourth is 5 cubed times 5, that's 30, which is 2 mod 7. 5 to the fifth is 5 times 30 is 10, which is 3 mod 7. And 5 to the sixth is 5 times 3 is 15, is 1 mod 7. So when I take the powers of 5, mod 7, I see that I have 1, 2, 3, 4, 5, 6. I have everything. So 3 is a primitive root, 5 is a primitive root, and they're exactly 2 primitive roots. So there aren't any more. Just as an exercise right now, find the primitive roots mod 5. The number is phi of 5 minus 1, phi of 4, which is 2. So they're going to be 2 primitive roots mod 5. So you should try to figure out what they are. Can anyone tell me what are the primitive roots mod 5? The non-zero congruence classes mod 5 are 1, 2, 3, and 4, plus 5z if you like.
2 and 3, Professor.
What?
2 and 3.
Well, 1 to the, so a primitive root mod 5, A is a primitive root mod 5 if 4 is the smallest number such that a to the 4th is congruent to 1 mod 5. So 1 to the 1 is congruent to 1 mod 5. So 1 can't be a primitive root because there's a power of 1 less than 4 that gives you 1. Right? But 3
No,
is...
I said 2 and 3.
Ah, sorry, I misheard. You are correct. So 2 and 3. Because each of these has order 4 mod 5. Those are the smallest. 4 is the smallest power of 2, which is 1 mod 5. And 3 is the smallest power of, and 4 is the smallest power of 3. That's 1 mod 5. That is correct. Thank you. There also is now a kind of number theoretical logarithm. Remember, the log of it of a number, let's say the base 10, is the smallest power of 10 that equals the number. And we can also talk about logarithms, but they're called indices, index. So let G be a primitive root modulo P. So if A and P are relatively prime, then there's an index, there's an integer A, K, which is positive, and if most P minus 1, such that A to the K is congruent to 1 mod P. We know P minus 1 always works, but we don't just want any K. We want a smallest k such that a to the k is congruent to 1 mod p, and k is called the index of k with respect to, k is called the index of a with respect to the primitive root g, or it's also called the discrete logarithm of a with respect to g. This is extremely important in computer science and many aspects of applied mathematics, this discrete logarithm, mod p. So for example, suppose we let p equal 13. Let's look for a primitive root mod 13. So let's try 2. So 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16, which is 3. 2 to the fifth is 2 times 2 to the fourth. 2 times 3 is 6. 2 to the sixth is 2 times 2 to the fifth, which is 12. 2 to the seventh is 2 times 12, which is 24, which is the same as 11, all mod 13. Haven't gotten to 1 yet. 2 to the eighth is 2 times 11, 22, which is 9. 2 to the ninth is 2 times 9, that's 18, which is 5. 2 to the 10th is 2 times 5, which is 10. 2 to the 11th is 2 times 10, which is 20, which is 7. 2 to the 12th is 2 times 7, which is 14, which is 1 mod 13. So 2 has order 12 mod 13. So 2 is a primitive root. And to find the logarithm or the index, we can make the following table. So for every integer a, from 1 to 12, a, and I want to know what is the index of a with respect to the primitive root 2. So actually, the smallest k can be 0, of course, because a to the 0 is 1. So if I take 1, let's say 1, 2, 3, 4, 5, 6, and then I'm going to need another table. 7, 8, 9, 10, 11, 12. So what power of 2 is equal to 1, the 0th power? What power of 2 is 2, the first power? What power of 2 is 3? 2 to the fourth is 3. So the index or the logarithm of 3 to the base 2 is 4. What power of 2 is 4? 2. What power of 2 is 5? 9. What power of 2 is 6? 5. What power of 2 is 7? 11. What power of 2 is 8? 3. What power of 2 is 9? 8. What power of 2 is 10? 10. What power of 2 is 11? 7. What power of 2 is 12? Here it is, 6. So I have all the integers from 0 to 11. Those are the different indices for 2. And so a basic calculation, one that you have to do in homework and that you'll have to do on the exam certainly, is given a prime p, find a primitive root, find all the primitive roots, and with respect to some particular primitive root, find the index of every non-zero congruence class. But this discrete logarithm is really important. It's the basis of all cryptography, all secure communications, all internet commerce, all cryptocurrencies. So, okay. Section 3.2, we're skipping, and section 3.3 is called power residues. And the definition is the following. Suppose we have an integer m at least 2, an integer k at least 2, and an integer a relatively prime to m. We say that, so this is the definition. A is a kth power residue modulo m if there exists an integer x such that, and this is the important congruence, x to the power k is congruent to a mod m. So if you take k equal to 2, a 2th power residue is called a quadratic residue. So this is just a special case of the definition. A is a quadratic residue modulo m if there exists an x such that x squared is congruent to a mod m. So x is like what you might call the square root of a. You're just trying to find the square root. So for example, if you have x squared congruent to 9, mod 13, and one solution is x congruent to 3 mod 13. Another solution is 10. 10 squared is 100. 100 minus 9 is 91. 91 is divisible by 13. So this is sort of saying that mod 13, the number 9 has 2 square roots, 3 and 10. Suppose we wanted to solve x squared congruent to, let's see, what's a good example? x squared congruent to 3 mod 13. Interesting.
4.
4, excellent. So if you take x congruent to 4 mod 13, x squared is 16, which is the same as 3 mod 13. And if you want another solution, of course, just as with the ordinary integers, you know, if 2 is a square root of a number, so is minus 2. So x congruent to minus 4 mod 13 would also be a solution, because if you square minus 4, you get 16, which is 3. And of course, minus 4 is the same as 9 mod 13. So the square roots of 3 mod 13 are 4 and 9. That's interesting. Yeah. So a quadratic residue is just the square root. And actually, for most of the rest of the semester, we're going to be studying quadratic residues. Also important, though it's going to be too hard for us to look at, is in the case when the power is 3, A is called a cubic residue, mod M. If there's a number x such that x cubed is congruent to A, mod M. So looking for quadratic residues, of course, you know that in ordinary arithmetic, not every number has a square root. Like -1 doesn't have a square root in the reals. So let's see. So remember, x is let's just look at an example. Quadratic residue A is a quadratic residue mod 7 if it's a square. If there exists an x such that x squared is congruent to A mod 7, A and 7 relatively prime. So let's ask the question, what are the quadratic residues mod 7? Does every number have a square root or only some? So let's see, the simplest thing to do is maybe just look at the perfect squares. So 1 squared is congruent to 1 mod 7. 2 squared is congruent to 4 mod 7. 3 squared is 9, which is congruent to 2 mod 7. 4 squared is 16, which is also congruent to 2 mod 7. 5 squared is 25, which is congruent to 4 mod 7. 6 squared is 36, which is congruent to 1 mod 7. So if you look at all the squares mod 7, non-zero squares, you get 1, 2, and 4 only. So 1, 2, and 4 are quadratic residues mod 7. But what about the other congruence classes, non-zero mod 7? 3, 5, and 6. Well, there's no number that you can square that gives you 3, 5, and 6. So we might say these are quadratic non-residues mod 7. So mod 7, there's 6 non-zero congruence classes, and exactly half of them have square roots. here's a little exercise. What are the quadratic residues mod 11, the next prime? So what are all the numbers relatively prime to 11 which have square roots? So you just have to do a calculation, which is take all the 10 numbers up to 11 and square them. 1 squared is 1. It's actually plus or minus 1. Plus or minus 2 squared is 4. Plus or minus 3 squared is 9. Plus or minus 4 squared is 16, which is 5. Plus or minus 5 squared is 25, which mod 11 is 3. So 1, 2, 3, 4, 5. 6 is the same as minus 5. 7 is minus 4, and so forth. So the quadratic residues mod 11 are 1, 3, 4, 5, and 9. So if I look at the other congruence classes mod 11, so these are the quadratic residues, 2, 6, 7, 8, and 10. These are quadratic non-residues. This says that there is no matter how hard you'll try, you cannot solve the congruence x squared congruent to 2 mod 11. This never has a solution. Okay. There's one theorem in this section that I want to prove, and then we'll quit for the day. If you have questions, I know there's an office hour tomorrow, I think at 1:30. And the class on Monday is a review class, so it's just going to answer questions and go over problems. But there's a lot here that we're doing today that to understand. So the one theorem in this section is the following. This is theorem 311. P is a prime number. K is an integer at least 2. And D is the greatest common divisor of K and P minus 1. And A is an integer, which is relatively prime to P. So we know that every prime P has primitive roots, that G be a primitive root mod P. A number relatively prime to P, is a kth power residue modulo P if and only if the index of A with respect to G is congruent to 0 mod D. So I want to know if a number A is a kth power residue. So I let D be the greatest common divisor of K and P minus 1. If the index of A is divisible by D, then the theorem says A is a kth power residue. And an equivalent statement is that if I take A and raise it to the power P minus 1 over D, which we know is an integer, this is congruent to 1 mod P. Oh. And how many kth power residues are there, if there are any at all? If A is a kth power residue, modulo P, then the congruence, x to the k congruent to A, mod P, we know there's at least one solution. And this has exactly D pairwise incongruent solutions, mod P. And how many kth power residues are there? So there's a lot in this theorem. I think maybe I'll wait till Monday to prove it. There are exactly P minus 1 over D pairwise incongruent kth power residues, mod P. So let's just look at the special case of quadratic residues and see what this theorem says. So quadratic residues, that's when you're taking the power k equal to 2. And P, let's say P is an odd prime, P equal 2 is not very interesting. If P is an odd prime, P minus 1 is even, 2 divides P minus 1, so D, which is the greatest common divisor of k and P minus 1, which is the greatest common divisor of 2 and P minus 1, is equal to 2. So this says that A is a quadratic residue if and only if the index of A with respect to a primitive root is divisible by 2, is even. If and only if A to the P minus 1 over 2 is congruent to 1 mod P, and there are exactly half P minus 1 over 2 quadratic residues, mod P. So when we're looking at quadratic residues, half of the non-zero congruence classes are quadratic residues, half are not. And we have a criterion for a quadratic residue. All right. All right, well, there's a lot to learn today, a lot to study. And are there any questions? I'm happy to explain things, but it's probably best if you find a quiet place where you can sit down with your book and notes and study what's going on and work out the exercises as much as you can and so forth. And that's where we are. What is always the goal of a first course in number theory is to prove what is called the quadratic reciprocity law. And which we will prove, in fact, just before Thanksgiving. Okay. If there are no questions, then we will stop for the day. Bye all.
Have a good day, Professor.
Thank you.